Jai Hind everyone. So this is the first lecture of register system design, and the topic we are going to cover is number system and binary codes. So coming to the common number systems, we have been using decimal from a long time since our schooling days, and the binary is the one which is being used by the computers, the machines, and octal and hexadecimal are the other numbers which act as interface between the human and the machine. So we have to understand what is the base of every number system. So base is the number of symbols which are being offered by a system, a number system. So by decimal we mean that it is offering us 10 symbols, binary is offering us 2 symbols, octal is offering us 8 symbols, and hexadecimal is offering us 16 symbols. So binary, we are all aware that the 10 symbols are 0 to 9. For binary, these symbols are 0, 1. And similarly for octal 0 to 7, similarly for hexa 0 to 9, and 10 to 15 are represented by A to F. So these are used by humans or not. Decimal is the one which is being used by humans. Anyone who is educated or not, he is using that number system, decimal number system. And from machine point of view, that means from computers, mobiles point of view, they are using binary as a communication mechanism between the various components. So we have to cover the different conversion possibilities between these number systems. So these are the 4 prominent number systems, and all the possibilities which exist between these are shown in this slide. So we will start covering these one by one. So this is very basic thing regarding the decimal number system. So how that decimal is being represented in different forms. 25 is in decimal, and if it is being converted into binary, it is shown as 11001, and in octal it is 31, and in hexa it is 19. Okay, so how these conversions are being possible, how these can be done? For this we are proceeding to our first set of conversion, and decimal to decimal, it seems innocuous that why are we going for this decimal to decimal. I mean, there is no sense of doing decimal to decimal conversion, but if we are doing this, then it paves the path for other conversions. Like we can see here that 125, now this 5 is having the place value of 10 raised to the power 0, 1's position, and 2 is having the 10's position, and 1 is having the 100th position. So 5 into 10 raised to the power 0, 2 into 10 raised to the power 1, 1 into 10 raised to the power 2. These 3 multiplications are yielding our products as 5, 20, and 100. So when we add these 3 numbers, 5, 20, and 100, I get the number as 125. So this same structure can be used for conversions between decimal to other number systems. So let's take an example of binary to decimal conversion. Okay, so technique is multiply each bit by 2 raised to the power n, where n is the weight of the bit. Weight means place value. Is it at the 1's position, 10's position, if we go by the decimal thing? But in binary, there is no 1's, 10's, 100. So we will be going by the weight, 2 raised to the power n. That means the least significant, that means extreme right, is having the weight 0, 2 raised to the power 0. So actually its weight becomes 1. Okay, and then we can add the results. So let's take an example. So this is an example in which we have to convert this binary number into a decimal number. So 101011 is a 6-bit binary number. So this here, let's hold on. If we go back to the previous slide, just hold on. This thing. So now this thing is your binary number. So it is having 6 positions. So these 6 positions we have to, this 1 is our LSB, and this one is our MSB. Okay, so if we use the same pattern in which we had used for the decimal, So we can see that 1 into 2 raised to power 0, 1 into 2 raised to power 1, and similarly multiplying these bits by the corresponding weights. Okay, and we are having different outputs. So like this, we have done 6 products, and when we add these 6 products, we are getting this output as 43. Okay, so this 43 is my decimal. Okay, so in this way we can convert a binary number into decimal number. Similarly, we can convert an octal number into decimal number. Let's check this, how this can be done. So the rule position are exactly the same. Like for binary, we had used 2 raised to power n, now we will be using 8 raised to power n. That's the only difference, and that's the same. So let's go for this actual conversion part. So 724 is the octal number, and we have to convert this octal number into decimal. So this 4 here is your least significant digit, and this 7 is your most significant digit. Okay, so this 4 into 8 raised to power 0, 2 into 8 raised to power 1, 7 into 8 raised to power 2. We can perform these 3 products and then add these, then we will be getting our answer as 460. So as simple as that, like we had done for the binary, this is for the octal. Now hexadecimal to decimal. So the rule position is again the same, just like for the binary we had used to use 2 raised to power n, like for octal we had used 8 raised to power n. Now for hexadecimal we are using 16 raised to power n. Okay, so proceeding further. So let's suppose ABC is the number in hexadecimal, and we have to convert this ABC into decimal. So now this C, for this we have to understand that this C is actually equivalent to 12, and this B is actually equivalent to your 11, and this A is actually equivalent to your 10. Okay, so that 12 into 16 raised to power 0 here, that C has been replaced by this 12. Okay, similarly B is being replaced by 11 and A is being replaced by 10, and we have multiplied it by the corresponding basis, 16 raised to power 0, 16 raised to power 1, and 16 raised to power 2. So further, when we add this, we get this decimal equivalent as 2748 in decimal. So this is our conversion from decimal. So decimal we had, these were conversion to decimal. We had moved from binary to decimal, we had moved from octal to decimal, we have moved from hexadecimal to decimal, and now we will be going from decimal. So the first one is decimal to binary. So the technique is just we have to divide by 2, or if we want to generalize this, then we can make it divide by the base. This 2 can be replaced by base. So in whichever number system you want to perform this conversion, just replace this 2 by that. So if you want to convert decimal into octal, then the rule positions are same, but 2 will be replaced by 8. Similarly for hexa, this 2 will be replaced by 16. So just the first remainder will be considered as the LSB, and the last one will be considered as the MSB. That means we have to arrange the remainders in the reverse order. Let's check this. So if 125 is in decimal and we start performing this successive division by this base 2, so 2 divided by 125 is 62 and remainder is 1. And similarly, if we keep performing these divisions, so we are getting these remainders, and we arrange these remainders in the reverse order. Reverse order means in this order. Okay, so in this order, if we arrange them, we are getting this as the binary of this 125. Okay, so this binary of 125 can be obtained from this. Okay, so let's move from decimal to octal. So the rule position, as we have already discussed, we will be dividing by 8 now, and we will be keeping track of the remainder. Let's check this. 1, 2, 3, 4 is in decimal, and we have to convert this 1, 2, 3, 4 decimal into octal. So we are dividing it by 8, continuously dividing by 8 and collecting the remainders. So 1, 2, 3, 4 divided by 8 is 154 and remainder is 2. Similarly, 154 divided by 8, remainder is 2. Okay. So, and when again these remainders are being arranged in reverse order, when this order. So these, if we arrange these in reverse order, we will be getting 2322. Okay, so this is conversion from decimal to octal. Similarly, for decimal to hexadecimal, we will be dividing by 16 and keeping track of the remainder. So 1, 2, 3, 4 in decimal, if we divide this by 16, we are getting 77 as the quotient and 2 as the remainder. And similarly, when we proceed further and divide 77 by 16, we get 4 as the quotient and 13 as the remainder. But we have to remind this that 13, this group, or this is now group of 2 symbols, but this is in, that 13 is in decimal. But this decimal has to be converted into hexadecimal. And for this 13, that 13 is represented by symbol D in hexadecimal. So we are replacing this 13 by D. So the sequence becomes like this. This 14 into this order. So reverse order, 4D2 becomes a hexadecimal conversion. Now for octal to binary. Now one possibility is that when we can move from octal to decimal, we have already done, and then we can move from decimal to binary. And this is something which we have already covered. So it can be either a two-way process, but there exists a direct method for octal to binary conversion. For this, we have to convert octal digit into each octal digit into its 3-bit binary equivalent. So if I want to represent 708 in binary and 705 is in octal right now, and if I want to convert this into binary, then I have to simply do this thing, like this 705 has to be, this 705 is in octal, and 7 is to be replaced by its 3-bit binary equivalent like shown here. 7 is 111 in binary, 0 is 000 in binary, and 5 is 101 in binary. And when we club these three conversions, then we get the binary equivalent of this 705 octal. Okay. Similarly, for hexadecimal to decimal. For hexadecimal to decimal, we will be converting each hexadecimal digit into 4-bit binary representation. Instead of 3, which we had used for octal, now we'll be using 4-bit binary equivalent representation. For example, if I want to convert this 10AF, which is an hexadecimal, into your binary, then I will be representing 1 in 4 bits. 1 in 4 bits can be represented as 0001, then 0 can be represented as 4 times 0, A can be represented as 1010, and F can be represented by 1111. Okay. So, and when we club these 4 conversions separately into one, when these 4 separate conversions are being converted into this one thing, so we get the final binary representation of this 10AF. Okay. Now binary to octal. Binary to octal is a reverse part, in which in octal to binary we had replaced each octal digit by 3-bit binary. So for going from binary to octal, we can group the bits in 3. Okay. If we group 3 bits and replace each 3-bit combination by an octal digit, we can get back to octal. For example, if this is the binary number which is being provided to us, so if I want to convert this into octal, so what I need to perform is, let's hold on. If I place 3 zeros here, sorry, 2 zeros. Now this 001 becomes your 1, and this 011 becomes your 3, and 010 becomes your 2, and 111 becomes your 7, and the answer becomes 1327. Okay. So now for binary to hexadecimal,